Hello, welcome to our pedigree analysis video. We'll be doing some practice problems, and this is for honors bio.
Okay, so I'm gonna go through a practice problem with you guys. Pretty much what I'm gonna use is a guess and check method almost. I'm gonna go through autosomal dominant, autosomal recessive, X-linked dominant, and X-linked recessive, and I'm gonna assume that the disease is the certain type, and then either I'm gonna prove it wrong or I'm gonna tell you guys that the answer is right. So let's start with autosomal dominant. So for autosomal dominant, we have to assume that the disease's genotype is going to be a dominant genotype. So let's say it's big A, big A. So obviously the recessive has to be the parents because they're not given the disease. But we already can tell that that's not going to work because the diseased genotype or the the dominant genotype can't be passed on from either of these parents. So we already can say that autosomal dominant isn't the answer. Okay, so let's move on to autosomal recessive. Let's assume that the genotype for the disease is recessive. So small a, right? So since small a is the genotype for the recessive, let's make the parents heterozygous. But see, we can already tell that this works because both of these genotypes are present in the heterozygous. So this is possible because the diseased offspring can get both of the recessive genotypes from the parents.
So, recessive allele, not the genotype.
I'm sorry, yes, the recessive allele, thank you.
Yes.
This works. Alright, so we'll keep that one in mind. Next is X-linked dominant, and this just means that the disease has to have at least one dominant allele associated with it. So let's say it was heterozygous. Even if it was just heterozygous, since both of these parents don't have the disease, they're both going to have the recessive alleles for their genotypes. So there's nowhere for the capital A, the dominant allele, to come from, so the disease can't present itself, which means that it can't be X-linked dominant. Next is X-linked recessive. So if it was X-linked recessive, we would assume that the disease's genotype would be both recessive alleles, right? But if so the parents are both going to be dominant alleles, so it'd be like that, and the female would also have the dominant allele. Even if it was heterozygous, we would get one recessive allele, but we don't know where the other one would come from because this is a Y. So the father is going to pass on a dominant allele. So there's nowhere for that second recessive allele to come from. So this also can't be X-linked recessive. So the only answer that we got that was right is going to be autosomal recessive. So that should be good. Alright, so we're going to put up a problem onto the screen. Once you see it, pause the video and try to go through the problem, and then once you think you're done, play the video and we'll show you guys how to do it.
Alright, now I'm going to do a practice problem with the X-linked traits. Oh, okay. So first I'm going to assume that it's X-linked recessive, so since the male parent of the first generation does not have the disease, his only X is going to be a big A, since he does not have the disease, and then he's going to have a Y. And the female who does have the disease is going to have two little a's because she has a recessive phenotype. So now we're going to look at their children, and this female has the disease, so both of her X's have to be little a's. And you can already tell that can't work because since the father gave his X, he couldn't give his Y, so he had to give his X. His only X is a big A, so he couldn't have given a little a, so X-linked recessive would not be able to work. So now let's assume that it's X-linked dominant. So the male who doesn't have the disease, he's going to have the dominant trait on his one X, and then he's going to have his Y, and then the female who does have it is going to have a big A, and then let's just give her a little a, the recessive. And then so their daughter who does have the disease can get a big A from dad and then a little a from mom. and that'd be okay. That'd still show the disease and the phenotype. And their son would have to get his Y from his dad, and he could get the dominant trait from his mom, and that'd show the disease as well. So that could work. And now the other son could get the Y from dad, and then it'd have to get the recessive trait from mom to not have the disease. So that could also work. And then the daughter would have to have two X's. We'd have to get the big A from dad, and then this would not work. So you can write, so right here it shows that since they'd have to get the big A from dad, and it could get a little a, that'd still show the dominant thing. So X-linked dominant would not work. And so now let's go to autosomal recessive. So the father is going to have a big A and then maybe a little a, and then the mom who has the trait is going to have two little a's. And so the daughter who also has is going to have to get the little a from dad and the little a from mom. That can work. And the son will also have to get two little a's. The son who does not have it will get the big A from dad and could get the little a from mom, and that would also work. And same with the daughter. So far so good. This could work. And so now we have someone marrying into the family. So let's just assume that they have big A, little a. Since they do not have the trait, they can have the dominant allele. And their son here could have the big A from their mother and the little a from dad. And then the daughter could get the little a from dad and the little a from mom, and that'll make her have the disease. Big A, little a, and then little a, little a. So this is going to be autosomal recessive. So we guessed and checked, and that is able to work. And that's our video on pedigree analysis. And
I hope that was helpful.